This video is a demonstration of basic functionality of the OpenCyphal version of Foucault Mini-Dyno benchtop dynamometer. And I will show how the Mini-Dyno maintains constant resistance level for the motor under test, and how it is maintaining constant resistance following the set point sent to the microcontroller of the Mini-Dyno from a controlling PC via OpenCyphal communication protocol. So here on the right I have a simple dummy motor under test. It is a brushed DC motor with an inline planetary speed reducer, and here on the right I have a laboratory regulated DC power supply. So I'm going to start running the motor, and we will be observing how the Mini-Dyno's variable air gap permanent magnet eddy current resistance unit responds to the motor's operation. All right, we will also be observing the display of the Mini-Dyno. Currently the torque set point, torque SP line is 0.005 Newton meters, or in other words 5 millinewton meters, and the initial gap right bottom corner of the screen is 5.00 millimeters. So this is the initial gap between the rotor is here on the right, it's a black disc, and the stator is the copper disc attached to this aluminium stator holder. All right, let's fire it up. I'm going to gradually increase voltage to the motor under test, and we already see that the stepper motor has begun to rotate, and it is adjusting the gap in order to maintain constant resistance level. And let's have a look at the screen, and we already see that the torque, measured torque that is received from the torque sensor DIN200 via Modbus, it's already here on the display. It's already 0.005 plus or minus 0.1 millimeter. Okay, so, and the current gap is, you can see it here, it is 4.68 millimeters, and it's really slowly adjusting, responding to, for example, slightly heating up or cooling down of the stator, depending, but as long as the motor will be spinning with a constant speed, and currently it is 288 RPM, the system is going to maintain constant resistance level. So let's also have a look at the torque sensor display. It's also showing 0.005 Newton meters, a little bit more jumpy display because this display is not showing filtered values, whereas the display of the Mini-Dyno shows slightly more filtered values for convenience of reading. Okay, let's spin it up a little bit faster to about 415 millimeter meters. And let's see what is going on. Well, it is already 0.005, so it has adjusted even without much delay, and the gap is now 5.65 millimeters. All right, let's try now to increase the set point to, for example, 175. It's going to be very hard for the motor. This is not a particularly strong motor, but again, let's see what will be going on the variable air gap stator side. Now it is adjusting, and let's see here. This is the most responsive display. So we are looking to get 0.0175, and on the display of the torque sensor we are already here, and let's see what a little bit nicer looking display is showing. And as you can see, the actual torque is already exactly the set point. Again, within 0.1 millinewton meters, it is maintaining constant resistance. And let's try some extreme step input. So we're going to reduce set point substantially down to say 0.0 perhaps 3. So it means 2.3 millimeter meters, and 1, 2, 3, go. It is still adjusting. It's not an easy task because we are at the lower end of the measurement and controlling range. However, we are still somewhere here. Again, the values are pretty jumpy on this display. So let's go back to the microcontroller's display of the Mini-Dyno and see what a filtered version of those values are showing. And here we go. Nice and steady. So even at the slower end of the controlling range and the measurement range of the torque sensor, we can maintain constant resistance really well, and the gap is fairly long, is 8.57 millimeters. So actually electromagnetic torque, electromagnetic braking at this distance is very small, but still the algorithm and the measurement system have sufficient capacity in order to provide for stable maintenance of the set point. And probably one last extreme demonstration. We are going to substantially load the motor, perhaps maybe overload. We are going to set 0.06, 60 millimeter meters, and we will see how the motor and the system will respond. So it's now 60 millimeter meters. Again, let's observe here. And now when the transition is really long, when the step magnitude is very fast, the initial movement is very, very fast. It makes this initial movement fast, and then it keeps adjusting. And we can hear how hard it is now for the motor under test to maintain this torque. And let's see what's going on here. Yeah, we're already there. We're almost there. Yeah, it's already there. And there you go. Now a little bit of, it may not be necessarily a steady state error, it's more like the motor itself has troubles maintaining a constant speed, even though we don't see it here because speed is filtered, but it is a little bit over 60 millimeter meters, but I would say like 60 millimeter meters plus or minus 0.1 millimeter meter is good enough. It's actually pretty good. And I will gradually start slowing the motor down and see what's going to happen. Now the system is clearly cannot move any closer because the current gap is extremely short now, it's 0.12 millimeters, and at this speed and at this gap the system cannot generate sufficient braking torque. The system is not going to go any further, so you can see here that the gap is extremely short, it's practically almost rubbing, but the mechanical design, everything is done such that it's not going to rub and it's not going to move any further if it can't. So, and in the control algorithm, 0.1 millimeter is the shortest distance, so we are sitting here at 0.12, so because the next controlling action would actually push the system beyond 0.1 and towards the contact, which we don't want. Therefore, the system is no longer maintaining the braking torque. So this was the demonstration of basic functionality of Foucault Mini-Dyno. Thank you for watching.